Hello, and welcome to my report on Lab3, the magnetic field of permanent dipole magnets. In this lab, we were asked to record the magnetic field at different distances on axis due to a permanent magnetic dipole, analyze the recorded data, measure the magnetic field at locations off axis, generate a computational model to represent the magnetic field due to a permanent dipole magnet, and compare our computational and experimental data. The first step in the process for this lab was recording the magnetic field at different distances. Using my magnet, smartphone, and a tape measure, I first located the magnetometer that is in my phone. To do this, I aligned the phone with magnetic north and placed the magnet perpendicularly to the phone. I then slid the phone up and down until the X component of the magnetic field was maximized, then rotated the phone 90 degrees and did the same thing to maximize the Y component. Having located the magnetometer, I then recorded the field strength of a magnet at a series of on-axis distances. For each field strength, I performed 3 recordings and took the average of the results. The recordings were done at distances which corresponded to a field strength of 20, 70, 120, 170, and 220 microteslas. In analysing these initial data, the spreadsheet we used to record the data also plotted the natural logarithm of the X component of the field strength against the natural logarithm of the distance to the observation location. From this graph and the associated line equation, we can see that the slope is negative 3.2. This value of slope corresponds to the rate at which the magnetic field strength drops off. We know that on axis, the magnetic field strength is the product of the magnetic constant and 2 mu over r cubed. This reinforces our experimental findings, as we expect the magnetic field strength to drop off like r to the negative 3. Another set of experimental data I recorded was the magnetic field strength off axis. I first placed the magnet a distance away which corresponded to a magnetic field strength of 100 microteslas. I then moved the magnetometer the same distance perpendicularly off axis. Here, I recorded each component of the field strength. We will use this data to compare the computational model I made to the real-world values. The next step was to produce a computational model for the field strength of a permanent dipole magnet. One of the values we need for the computational model is the magnetic dipole moment, mu. To calculate this, I took the equation for the magnitude of the magnetic field strength of a dipole on axis and rearranged for mu. I used the average values for each of the 5 locations I measured the field strength at and calculated mu for each of them. These values range from 10.9 to 12.9 using the different data. I then took the average for a value of 11.7. Next, I began working on the code. The first thing to do was to create a function dipole B to calculate the magnetic field strength at a location given a magnet's magnetic dipole moment and an observation location. Following this, the majority of the changes in the code were to display an arrow indicating field strength at different locations. 2 of these were on axis and an equal distance in the positive and negative x direction. The next 4 arrows were perpendicular to the dipole and also at the same distance. Rather than creating 4 different arrows in code, I used a simple loop to produce these ones. The last arrow is used to visualize the magnetic field strength at 45 degrees off axis. Here is the output for my computational model. From the arrows on axis and perpendicular, we can see that the magnetic field is being represented well. This particular model has the observation location of all the arrows set to 0.47 meters, which is the distance at which we expect to see the magnetic field strength. The magnetic field have a strength of 2 times 10 to the negative 5 teslas on axis. And we can see the computational output is not far different. Looking at the 45 degrees off-axis observation location, we see there is a discrepancy in the calculated and recorded magnetic field, but this is likely due to an error in the recording of the off-axis values. Lastly, we have the final questions. The first asks what happens if we didn't align our magnetometer with magnetic north. This would skew our data to include the Earth's magnetic field too. We could account for this and subtract it out of every recording, but by aligning them orthogonally, we can deal with them we can record them separately. The second question asks, what if we stick 2 magnets together and run the experiment again? By doing this, you would almost double the magnetic field strength at any given point, as you would effectively be superposing 2 identical fields. However, they would be slightly displaced as they can't exist in the exact same location. Thank you very much for listening to my report.